So, hello students. Today we are going to continue our discussion that we started from our last class, and we were discussing about thermodynamics and also discussing about the enthalpy and how a enthalpy of reaction can be calculated. We also saw that for a specific chemical reaction, if we consider the different delta H formation values, we can calculate the del R H value at the standard state of the reaction. And we saw some examples. Today we will talk about the Hess's law of summation of heat. And before going to the details of what is meant by Hess's law, we will see some specific examples for your illustrations so that you can have a better grip or better understanding on the calculation of enthalpy of reaction and a thermochemical equation. So we will start today's discussion with thermochemical equations. So let's see over here. You might have heard this term, this thermochemical equation. So what is meant by this term, the thermochemical equation? I guess you all have heard about a chemical reaction. So a chemical reaction is where we have some reactants, they react at a certain condition and they produce some products. And whenever we talk about a chemical reaction in thermodynamics, it is very important to balance the reaction. You have seen, might have seen in all the numerical examples I have shown to you so far, in all the cases, I have tried to balance the chemical equation first and then carried out the next numerical solutions. So when a balanced chemical equation is there and it is clubbed with the value of the del R H, that is the reaction enthalpy value, then it is called a thermochemical equation. So firstly, we need to have a chemical equation which should be balanced. And also, we have to mention the del RH value of the reaction. That is the reaction enthalpy value. So, a balanced chemical equation together with the value of the del RH value, that is the reaction enthalpy value, is termed as a thermochemical equation. So, whenever you are asked what is meant by thermochemical equation, you will write the entire balanced equation, and on the right hand side at the very end you will write the del RH value in kilojoule per mole preferably. So this total is termed as thermochemical equation. Now, in thermochemical equation, we have to specify the physical state along with the allotropic state of the substances also. So, for example, if you are talking about some reactants like alcohol or any gas, we have to mention it is liquid or it is solid or it is gas. Also, we have to mention the allotropic form also. You have known about allotropes like sulfur, carbon. These remain in many various forms of allotropes. So if it is in a specific allotropic form, we have to specify that also. For example, if we take up the reaction, the burning of ethanol at air. So we have ethanol, and since it is a liquid, we have to mention the physical state, that is liquid over here. And if it is burnt in oxygen, 3 O2 and it produces 2 moles of CO2. Oxygen is a gas, and that's why the physical state is mentioned as G. 2 CO2 gas plus 3 H2O liquid, since water is liquid at room temperature. So we have the total balanced equation, but this equation is not a thermochemical equation, because I have told you a chemical equation which is in balanced form and along with the del RH value, that is the reaction enthalpy value at the standard state, will be termed as the thermochemical equation. So to make it a thermochemical equation, we have to provide the del RH value. So in this case, the del RH value, that is minus. Minus stands for the standard state, is minus of 1367 kilojoule per mole. So we have this equation, C2H5OH ethanol plus 3O2 in gas will produce 2 moles of CO2 and 3 moles of water. This above equation is actually describing the combustion of liquid ethanol at constant temperature and pressure. The negative sign that is here, the negative sign is actually indicating that this is an exothermic process. So heat is generated from the reaction. Heat is not required for the reaction. So it is very necessary to remember the following conventions. The first convention is the coefficient in a balanced thermochemical equation refers to the number of moles and not molecules of the reactants and products involved in the reaction. Many of times you guys make this common mistake, like this is not a molecule, this is number of moles. So 3 moles of O2, 1 mole of ethanol will produce 2 moles of CO2 and 3 moles of water. The second one is the numerical value of del RH minus refers to the numbers of moles of substances specified by an equation. The standard enthalpy change, that is del RH minus, will have the same unit as kilojoule per mole. And also the numerical value suggests for the moles of substance specified. So for 1 mole of ethanol, the value is minus 1367 kilojoule per mole. So for 3 moles of oxygen, the value is minus 1367 kilojoule per mole. So this is all about a thermochemical equation, but to illustrate it more vividly, we have to take up another example and we will see how from a thermochemical equation we can derive the data. So we will start with a fresh equation, a fresh thermochemical equation. So let me write the hydrogenation of ferric oxide. So to form iron and water. So we have the reaction Fe2O3. Fe2O3 is iron oxide and it is a solid substance. So we will write S. It is burnt in presence of dihydrogen. It is a gas, so we will write it as H2 gas. It is actually a reduction procedure. So Fe2O3 in presence of molecular dihydrogen will be reduced to Fe solid. Iron is also a solid in its elemental form. And as a byproduct, we have the H2O, that is liquid at room temperature. So not only a chemical, it is just a chemical equation. For to make this chemical equation a thermochemical equation, first we need to balance it. So we will balance this. We see over here there are 3 oxygens on the left hand side. There are 1 oxygen on the RHS. So we'll first put 3. over here. Now the number of hydrogen becomes 6. So here we have to make it 6. And also there are 2 moles of Fe on the left hand side. So on the RHS, we will also have 2. So now this equation is balanced. Now we have in the last class from the standard enthalpy of formation, we need the value of standard enthalpy of formation, that is the delta FH minus value. So if we go back to the table that we discussed in the last class, here I guess you guys remember these are the standard molar enthalpy of formation, that is delta FH minus at 25 degrees Celsius for few selected substances. Here, if we see the delta FH minus of water is given here, which is of H2O liquid minus 285.83 kilojoule per mole. Also, we have here the delta FH minus is equal to minus 824.2 kilojoule per mole. If we search here, we will get the Fe2O3 value too. The Fe2O3 value will be minus 824.2 kilojoule per mole, which is over here. So we have 2 values already, the H2O liquid, Fe2O3. Also, we need the values for hydrogen and also the values for iron. Now, in this class, I have actually told you like whatever be the substance in standard form, it will be 0 of the delta FH minus if it is only monoatomic. Now, iron it is in a solid state and dihydrogen is also in its solid state. These two are in dihydrogen in its gaseous state. So these two are actually in their standard states. And as per the convention of the standard molar enthalpy of formation, these two values will be equal to 0. So now let's check over here. Firstly, we have the delta FH minus value of this we require. So firstly, we have the delta FH minus value and then we'll have the component. The substance is over here. So the substance on the left hand side, we have 4 substances, 2 products and 2 reactants. Among these, Fe2O3 and 3 or H2O, we have to have the value of these 2 products of reactants and products from the table. So for Fe2O3, the value is minus 824.2 kilojoule per mole. For H2O in its liquid form, the value is minus 285.83. And for the rest of the substances that are involved in the reaction, I have told that they are since their elemental state and they are in the standard state, so their enthalpy of formation value at standard state will be equal to 0. So for iron solid and dihydrogen gas, these values are 0. Now we have the delta FH minus values of all the substances that are involved. Now we have to apply the equation of del RH minus over here. So del RH minus, that is the reaction enthalpy at standard state, is thus equal to the summation of the coefficient and the molar enthalpy of formation of the products minus the summation of coefficients multiplied by the del FH minus of the reactants. Now on the reactant side, on the product side, we have iron solid, which has a zero value, and also the water value. So we need to multiply 3 into that of the enthalpy of formation of water. So water's enthalpy of formation is minus 285.3. So we have 3 into minus of 285.3 minus that of the value of the reactants. So in the case of the reactants, we have 1 mole of Fe2O3 multiplied by its molar enthalpy of formation, which is 324.2. If we solve this equation, we will get the del RH minus, we will put a subscript over here. Del RH1 minus will be minus 33.3 kilojoule per mole. So you have to see that the coefficients that are used in the calculations are pure numbers that are 3 and 1. Now these are actually equal to the respective stoichiometric coefficient. You see the 3 is coming from these 3 in the equation. Also this 1 comes from here, Fe2O3. So the unit for del RH minus will be kilojoule per mole. That means it is per mole of reaction. So once we balance the chemical equation in another way, that is another particular way, we will see as above, this defines the mole of reaction. So if we had balanced this equation in a different manner, let's say we are balancing this equation in a different manner. So let me write the equation again for your convenience. We have Fe2O3. I will not write the physical state over here, otherwise it will be very much boring. So Fe2O3, we have H2, we have iron over here, and water. So here, if we can balance the equation in different way, let's say on the right hand side, we have iron, 1 molecule. On the left hand side, we have 2 molecules. So let me put a half over here. So the iron becomes 1. All right. And now we have to make the oxygen also 3 by 2. Here oxygen is 1. So we have to multiply this by 3 by 2. So if I make it 3 by 2, oxygen will be 3 by 2 on both sides, but then the hydrogen will be 3 hydrogen. So then also you have to multiply it by 3 by 2. So now we have balanced this equation. Now this amount of reaction would be 1 mole of reaction, and del H minus 2 will be something different. So in this case, since the entire equation is divided by half, we will have the del RH 2 minus value equal to minus 16.6 kilojoule per mole. So that will be actually equal to just half of the del RH minus. So it is quite evident from this experiment that enthalpy is an extensive quantity. Its value actually depends on the stoichiometric coefficient of the reaction that we are talking about. So in the first case, when we balance the equation in a manner, we got the reaction enthalpy as minus 33.3 kilojoule per mole. And also in the second case, when we balance the equation in a different manner, we got the del RH2 minus as just half of the del R H1 minus. So this actually shows that enthalpy is an extensive quantity, not an intensive quantity. Another thing that is very much useful for you to know about the enthalpy case, that when a chemical equation is reversed, when we are reversing the equation, the value of the del R H minus remains the same, but it just gets reversed in sign. So for example, if we take this classical reaction of N2 gas plus 3 moles of H2, which is also a gas, and it produces 2 moles of ammonia. Which is also a gas. So del R H minus value of this reaction, forward reaction, will be, so let's say it is a forward reaction and it is a backward reaction. So for forward reaction, we have the delta R H minus forward. And for the backward reaction, we have the delta R H backward. So the forward reaction is N2 gas plus 3 moles of hydrogen producing 2 moles of ammonia. And the backward reaction is 2 moles of ammonia giving rise to 1 mole of N2 and 3 moles of H2. So if we have the value del R HF minus as minus 91.8 kilojoule per mole. So it is quite evident that the value of del R HB minus, this value, will be just the opposite, because it is the reverse reaction of the first one. So it is plus 91.8 kilojoule per mole. So the value remains same, but the sign gets reversed. So these are some important corollaries from our thermochemical equation that we learned in this. And next we move to the next important part of our discussion, that is Hess's law. Hess's law of constant heat summation. Now, Hess's law of constant heat summation, or just Hess's law, states that regardless of the multiple steps or stages of a reaction, the total enthalpy change for the reaction is sum of all the changes. This law is a manifestation that enthalpy is a state function. So the enthalpy value does not depend upon the path or the route taken. So does not matter whether there are multiple steps, or does not matter whether it is single step. The total enthalpy change for the reaction would be same, and it will be summation of all the changes. So this law is a manifestation that it is a state function. So introduction, on the introductory part, I will tell that Hess's law is named after a Russian chemist and a doctor whose name is Germain Hess. And under his name Hess, the law is popularized as Hess's law. Now Hess helped formulate many principles of thermochemistry. The most popular paper, that is published in 1840, was in his law of thermochemistry. And his law is due to because enthalpy is a state function, which allows us to calculate the overall change in enthalpy just by simply summing up the changes for each step of the way until the final product is delivered. Now all the steps have to proceed at the same temperature, at the same equations. For the individual steps must balance out. We have to remember that all the steps have to be combined or proceeded at a similar same temperature and same pressure. No change is invited. And also the equations should be balanced in such a manner that all the individual steps can get cancelled out. The principle that is underlying the Hess's law does not just apply to enthalpy only. It is a separate case that Hess's law started with the characterization of enthalpy, but it can be used to calculate the other state functions too. So it is a generalized law now to calculate the other state functions like entropy or Gibbs free energy, enthalpy, and so on. So the heat of any reaction, that is the delta HF minus or zero for a specific reaction, is equal to sum of the heats of the reaction for any sets of reaction, which in sum are equivalent to the overall reaction. But I guess if you have to understand Hess's law well, we have to carry out our discussion by taking up a very good example, and then only we can understand what is actually meant by this Hess's law. So if a reaction is taking place in several steps, suppose from A to B we are going. So we have A in a state, we have B in another state. So from A to B, suppose we are not going via a single step. Meanwhile, we have these steps A2, A2, A2 to A3. Then we are going to B2, and finally we are going to B. So this is one process where A to B is single step, and from A to B we can go via A2, A3 and B2, such multiple steps. Now the Hess's law states that the standard reaction enthalpy is the sum of the standard enthalpies of the intermediate reactions into which the overall equation may be divided at the same temperature. So this must be ensured that at same temperature and pressure these reactions are taking place. And also from A to A2, A2 to A3, A3 to B2 and B2 to B, the sum of the enthalpies will be equal to the sum of enthalpy from A to B. So with the help of an example, we can actually understand what is meant by this. Now we will consider the enthalpy change for the reaction, that is carbon plus oxygen giving rise to carbon monoxide. So we'll start with a very simple example. So we have this carbon, that is graphite, in its solid state. Plus O2. Producing CO, that is a gas. So we have to calculate the del RH minus of this step, or you can say the process. What is the del RH minus? Also, before performing anything, as I have told you, for any reaction that we will work with, we have to first balance it. So here also we will balance it. We see the both of the number of carbon atoms is 1, but here oxygen number is 2 and here it is 1. So we will simply put a half over here. Now the equation is balanced. On the both of sides, we have 1 carbon atom and we have 1 oxygen atom. Now let's come to this specific example. We have the C plus half O2 producing CO in its gaseous form. Now, although CO is the major product, it is always there that some carbon dioxide gas is always formed in the reaction. Therefore, we cannot measure the above enthalpy change for the reaction directly. However, if we can find some other reactions involving related species, it is possible to calculate the enthalpy change for the above reaction. So let us consider the following reactions. We have carbon graphite solid plus O2 gas to CO2. So we have to take up another chemical equation. I will not specify the states over here again because of our convenience only. So graphite, if it can burn in oxygen, it can produce CO2. The del R H minus value of this is minus 393.5 kilojoule per mole. So let's name this equation as equation 1. Let's take up another equation where CO in presence of dioxygen produces CO2. The del R H2 minus value of this reaction is given, which is minus 283 kilojoule per mole. So now the problem started with the reaction of carbon in graphite from burns in dioxygen to produce CO, which is an incomplete combustion. The del R H minus value we have to calculate. But since this value cannot be calculated directly, we have got two equations. Equation 1 is C plus O2 to CO2. Del R H1 minus is minus 393.5 kilojoule. We have another equation where CO is burnt in dioxygen to produce CO2. The del R H2 minus value is minus 283 kilojoule per mole. Now we can combine these above equations in such a manner that we can obtain the desired reaction. So to get 1 mole of CO2 on CO gas on the right hand side, we have to reverse the equation 2, and then we can easily calculate it. So you see over here on the left hand side we have got C plus half O2. So we have to put these two equations or use these two equations such that we will get carbon on the left hand side. So we will put carbon on the left hand side. Now see here on this both right hand sides we have got this CO2, but we have to get rid of CO2 because in this equation we have no CO2. So to get rid of CO2, we will just reverse the reaction. And as I have told you in the last corollary, that for the reverse reaction, the enthalpy of the reaction will just be the positive one. So if we reverse the reaction, we have CO2 forming CO plus half O2. And for this reaction, the del RH3 minus value will be just the opposite one from the or the negative sign of the equation 2. So we have del RH value as plus 283. We will name this equation as equation 3. So now let's have a look at equation 1 and equation 3. On the equation 1, we have on the RHS CO2. On the third equation, we have CO2 on the LHS. So these two will be cancelled out. And if we see that we have oxygen over here, 1 mole, and we have half mole of oxygen on the right hand side. So here, if this half oxygen comes to the left hand side, we will get only half of oxygen. So let's add equation 1 and 3. So here if we can add equation 1 and 3 on the LHS, we have C plus O2 plus CO2. On the right hand side, we have CO2 CO plus half O2. So here we can see in the left hand side we have CO2, on the right hand side we have CO2. So these two CO2 gets cancelled out. And this half O2 can come to the left hand side. We have 1 mole of O2 over here. And if we minus one half from 1, we will have half. So ultimately we get the final equation that is required over here, which is C plus half O2 producing CO. And so we have added these two equations 1 and 3. So now we have for 1 the del H value as minus 393.5, and we have the del H3 minus as 283. So we have to add these two values, and ultimately we have got the value of del H minus as minus 110.5 kilojoule per mole. So I guess with this numerical example, you have got what is meant by the Hess's law of constant heat summation. So in general, if enthalpy of an overall reaction, let's say from A to B, we are going to the root that is del H, and then we have other roots also where we have del H1, del H2, del H3, and so on. So representing the enthalpies of reaction leading to the same product where B along is another root, then ultimately we have the del H value as summation of del Hi, where I is equal to 1 to n. So del RH value, the reaction enthalpy value, will just be equal to the summation of del RH I. So these also can be represented pictorially. So let's come over here for your easy understanding what the application is required. So hydrogen gas is very much useful in our daily life because it is of a potential interest nationally, because it is a clean fuel. As a fuel, it can be used to burn for our cooking purpose, for in our cars also, for our transportation system. And it can be generated by the reaction of carbon, that is coal, in water. So this is the reaction we are talking about. Carbon solid plus 2H2O gas will produce 1 mole of CO2 gas and 2 moles of H2 gas. Now calorimetry actually tells us that a reaction requires the input of 91 kilojoule of heat per mole of carbon consumed. So this is an endothermic reaction where 90.1 kilojoule heat is required per carbon mole. Now, by convention, if heat is absorbed during the reaction, because heat is required, we consider the quantity of heat to be a positive number because it is an endothermic reaction. And that's why Q is greater than 0 for an endothermic reaction. But when the reaction's heat is evolved, it is termed as an exothermic reaction. And then we will have Q less than 0. Now, it is interesting to ask where this input energy goes when the reaction occurs. This question may arise in your mind that this energy I am putting in, where is it ultimately hitting at? One way to answer the question is to consider the fact the reaction converts one fuel, that is carbon solid, into another fuel, that is dihydrogen gas. Now, to compare the energy available in each fuel, we can measure the heat evolved in the combustion of each fuel with 1 mole of dioxygen gas. So we have this fuel C plus O2 to CO2, which is one fuel reaction where carbon is burnt in oxygen to produce CO2, which produces 393.5 kilojoule for 1 mole of carbon burnt. So here the Q, since the energy is burnt, will be negative, and that's why the value here is minus 393.5 kilojoule. Now we have another fuel, that is dihydrogen. So if dihydrogen is burnt in oxygen, it produces water. And also in this case, it produces 483.6 kilojoule for 2 moles of hydrogen gas burned. So Q here is minus 483.6 kilojoule. But look at the balanced equation over here. It is for 2 moles of dihydrogen. And first one was 1 mole of carbon. Now it is evident that more energy is available from the combustion of dihydrogen fuel than from the combustion of carbon. So it is not surprising that when we are performing the conversion of carbon fuel to dihydrogen fuel, it requires the input of energy. So that's why, since dihydrogen produces much amount of energy than that of carbon, so when we are producing a hydrogen fuel from a carbon fuel, we will see there will be some input of energy. That is termed as the endothermic reaction. That is the speciality of an endothermic reaction. Now we have to consider the fact that the equation, heat input in the equation 2, that is 90.1 kilojoule, is exactly equal to the difference between the heat evolved, that is minus 393.5 kilojoule in the combustion of carbon, and the heat evolved, that is minus 483.6 kilojoule, that is the combustion of hydrogen. This is not a mere coincidence. If we take the combustion of carbon and add it to the reverse reaction of the combustion of hydrogen, we will also get that it is just the equation 2. So this also is case just I taught you in the last slide, that is the consequence of Hess's law of constant heat summation. So here you can say for this reaction we have the value minus 393.5 kilojoule. For this second reaction, we have the value of minus 483.6 kilojoule. Now, if we have to have the difference between these two, we'll end up in this 90.1 kilojoule of heat. That is for the endothermic procedure for the carbon to hydrogen fuel test. It is not a coincidence. If we have the equation 1 as C plus O2 and CO2, and the next equation we have 2H2 plus O2 to produce H2O. Now look at these two equations. In these two equations, if we have to cancel out the oxygen part, we have to reverse it. So we will reverse it, 2H2O producing 2H2 plus O2. Now we will add these two equations. We see this oxygen on the left hand side and oxygen on the right hand side gets cancelled out. And we end up getting C plus 2H2O producing CO2 plus 2H2O, which is just equal to the first equation that we are talking about. So cancelling this O2 from both sides, since it is neither a reactant and not a product. So equation 5 is actually equivalent to equation 2. So now if we have the reverse reaction, for the reverse reaction, we have the value as plus 483.6. And the forward reaction, we had this value. So we now have these two values in hand. First one is the minus 393.5 and the last one as plus 483.6. Now we have to add these two equations and their enthalpy values. So if we add these two, we end up getting 90.1 value. 483.6 minus 393.5, we have the value of 90.1. And the heat of combustion of carbon minus the heat of combustion of hydrogen equals to the heat equation. By studying many chemical reactions in this way, we can discover this result. That is the Hess's law. It is general and it is not only applicable for enthalpy, it is applicable for any state functions in thermodynamics, just as internal energy, just as Gibbs energy and entropy. So finally, this can be concluded with a pictorial diagram for Hess's law. So now if we have a procedure where we are going from a state A to state B, what we learned in this class that I am going to summarize over here. We have A and we have B. These are two independent states. And we have to go from A to B. So there can be several ways where we can go from A to B. One is the direct route. And for the direct route, the value of the reaction enthalpy is termed as del RH. Now let's take another route where we will stop at multiple positions. So that will be a multiple step reaction. So from A, we will first go to C, another independent state. And then from C, we will go to another step, that is D. From D, we will go to E, which is another state. And finally, from E, we will go to B. Now, these are individual steps. Now, for each step, let's define the reaction enthalpy value. This one is del RH1. For this step, it is del RH2. For this step D2E, that is del RH3. And for the final step of E to B, we have del RH4. Now, according to the Hess's law, if we have the reactant and product intact, and let's say the entire process is carried out at a constant temperature of capital T, then del RH value will be equal to the summation of all these values. It will be del RH1 plus del RH2 plus del RH3 plus del RH4, which we can write in a short manner by using the summation sign. It is del HI summation I equal to 1 to 4. So this is the mathematical representation of Hess's law. Hess's law of constant heat summation tells us that from del RH, if it is the total value enthalpy, and we have multiple stops or steps where we have individual del HI values, then the total del RH value will be the summation of all the individual step del HI values. So with this, we will conclude today's class. And if you have got any question or query, you can go ahead and ask regarding any of the slides.